Okay, so section 2.9 is called Dimension and Rank. This is a more theoretical section rather than a calculational section. And it's really just a couple of quick things here. The first is, what does dimension mean? The dimension of a vector space is the number of vectors in the basis. So in the last section we learned how to find the basis, and we had written out what the basis was. Now we don't even care exactly what the basis is. All we care is how many vectors there are. So one of our examples earlier, 1, 2, 3, 4, 5, 6, 7, 8, 9. That was the one from section 2.8. What we ended up getting was the basis for the null space was the vector 1, negative 2, 1, and the basis for the column space was 1, 4, 7, 2, 5, 8. And so what that means is that the dimension of that null space is 1, again, because there is literally one vector here. On the other hand, the dimension of the column space would be 2, because there's 2 vectors there. So all you have to do is count how many vectors are in the basis, and that will give you the dimension of that particular space. And just to get things more complicated, and I didn't do this, I'm not the one that came up with this, but the dimension of the null space, we call that the nullity, and the dimension of the column space, we call that the rank. And we could go into a whole story about why they're called that, but it doesn't really matter for us. Just know that sometimes when I write the question, I might ask what is the rank or what is the nullity, and that just means the dimension of the corresponding space. And once we have all these words here, we can give a really big theorem for this class. It's called the rank nullity theorem. And what this is going to say is, if A is an m by n matrix, then if you add the rank of A plus the nullity of A, you are going to get n. And at first this might seem like some crazy theorem coming out of nowhere, but it really isn't. You just need to think back to what we were doing earlier. Remember when we had pivot columns? Pivot columns became things in the column space, and the ones that were not pivot were free, and that's what we got, things in the null space. And so in general, if you think about taking all the pivot columns and all the columns that are free, that's just going to be all the columns period, which is n. This is the number of columns. So at first this is an interesting result in that it just comes out of nowhere, but it's actually very trivial to prove by just counting how many columns you have and saying each one's either a pivot column or a free variable column. And the reason why this is important is it helps us determine things without even knowing what properties may have. So for example, we're about to do the invertible matrix theorem, and you may remember the beginning of that we saw already was that if A is invertible, then AX equal to B has a unique solution. And that's, if you think about it in terms of AX equal to 0, if it can only have one solution, well, that one solution would be the 0 vector. And if that's the case, then that means your nullity is 0, because there's nothing in the basis for the null space. So that goes ahead, and once we know the nullity is 0, that gives us this result here. And so that means you have an invertible matrix if and only if the nullity is 0. So what if I told you that A is a 3 by 5 matrix. Now I don't know any of the numbers at all. All I know is that there's going to be 3 rows and 5 columns. Well, if that's the case, the most pivots you could possibly have are 3. That's the most ever possible here. But that means you're guaranteed to have at least 2 free variables. And if you have 2 free variables or any free variables, that means your nullity is at least 2, which means your nullity is not 0, and that means your A is not invertible. So right away, I mean, you can get information about what's going on here without ever knowing what the matrix is. So again, it's showing you the power of theoretical concepts here, that we can answer a question about what's going on without actually knowing the specific function we have, right? We're not doing any specific calculations here. We don't have specific matrix. We don't have a specific, row operations, but we can still answer a question about this and say it's not invertible. That's just one small example of what this can do. So it's trying to show you the power of theoretical thinking. Okay, the only other thing in this section is called the invertible matrix theorem. And it's probably the single most important linear algebra theorem in this whole class. And so I will go ahead and do this for you. Now, what this thing starts out with, it says TFAE. Mathematically, it's shorthand for the following are equivalent. And what that means is that I'm going to give you a long list of things here. And if any one of them are true, then they are all true. And if any one of them are false, then they are all false. So the first thing I will say is A is invertible. All right, so if you have an invertible matrix, that is the first condition that we are going to talk about. Well, another one is going to be that AX equal to B has a unique solution for every B. This was the actual condition I had in the previous, I think it was 2.2 section, that if you have any B at all, you're always going to have exactly one solution. Related to that, well, what if we have 0 here has only x equal to 0 as a solution? Okay, well, that means that the null space is just the 0 vector. Well, that means that the nullity is 0. And then by the rank nullity theorem, that means the rank is the number of columns, which we'll call that n here. So A is going to be an n by n matrix. Well, if the rank is n, then that means that the dimension of the column space is n. Turns out that means that the column space is going to be all of Rn. That also means that the columns are linearly independent. And honestly, I could keep going on here. There's actually like 15 or 20 different things I could write down here that are all logically equivalent to this. We don't need all of them. But the main things here is that when you have an invertible matrix, you have a unique solution, and that tells you information about the rank and the nullity. And so those are the ones we're going to get to. So I will tell you this, the way I phrased a question on this last semester was give me 3 equivalent conditions on the invertible matrix theorem. So in that case, I'm not asking you to memorize all of the possible things here, and there are a lot of them, but you should be able to at least know 2 or 3 off the top of your head so that you can kind of go back and forth. And the reason why that we use it a lot in this class is finding out whether a matrix is invertible is going to be based on something called the determinant, which we haven't talked about yet. And if the determinant is not 0, then it's going to be invertible. So in fact, that would be one of the other numbers on here. And once we know that, the determinant is actually another thing we can do in our calculator really easily. So if you are ever trying to solve any type of problem involving any of these things here, you can just put your matrix in your calculator, hit the determinant button, and if you get 0, then all of these things are false. And if you get anything other than 0, then all of these things are true. So again, it's trying to show this from a theoretical point of view and